Hi everyone, welcome back to another exciting math lesson. Today, we're going to dive into the world of transcendental functions and see how they apply to real life situations. We'll also explore how limits help us make sense of these functions in practical contexts. But what are transcendental functions? Let's start with a quick breakdown. Transcendental functions include exponential, logarithmic, and trigonometric functions. Today, we'll focus on these functions which are used to model real-world phenomena like population growth, diminishing returns in business, and even changes in natural processes like tidal heights. Let's start with population growth. Imagine a city whose population grows exponentially, modeled by the function p of t equals 5000 e raised to 200 t, where p of t represents the population after t years. Assuming no external factors limit growth, what happens to the population as time goes on and t becomes really large? In other words, what's the limit of this population as t approaches infinity? Since the population function is an exponential function, then the function has an increasing trend. With this, we can say that as t approaches infinity, the population will grow without bounds, meaning it approaches infinity. This means that, according to the model, the population will grow indefinitely over time. However, in a real-world context, factors such as limited resources, space, and environmental constraints would eventually slow down or stop the growth, even though the mathematical model suggests unbounded growth. Now let's look at logarithmic functions. In economics, logarithmic functions often model diminishing returns. What does this mean? It means that after a certain point, increasing production doesn't result in proportional gains in profit. For example, a manufacturing company has been increasing its production of widgets. The company's profit P of X from producing X widgets is modeled by the function P of X equals 500 times the logarithm of X plus 1, where P of X is the profit in 100 pesos and X is the number of widgets produced. Find the maximum profit of the company if they will produce about 99 widgets, and determine the maximum profit the company can expect if production continues indefinitely. To find the company's profit if they produce about 99 widgets, we use the limit of p of x as x approaches 99. That is the limit of 500 times the logarithm of x plus 1 as x approaches 99. Substituting x equals 99 into the function, we will have 500 times the logarithm of 99 plus 1. Simplifying, we will have 500 times the logarithm of 100. Using the fact that the logarithm of 100 is equal to 2, since 10 squared is equal to 100, we will have 500 times 2, which is 1,000. Since P of X is the profit in 100 pesos, we multiply 1,000 by 100. So the expected profit for producing about 99 widgets is 100,000 pesos. Let's verify our answer by analyzing the graph of P of X. In the graph, as x approaches 99, P of X gets closer to 1,000. Thus, the expected profit for producing about 99 widgets is 100,000 pesos. But what happens if the company keeps increasing production indefinitely? To answer this, we have to find the limit of p of x as x approaches positive infinity. By analyzing the behavior of the function, we can conclude that the limit of p of x as x approaches positive infinity is positive infinity. But take note that the logarithmic growth is very slow. This does not mean that the company will continue to see proportional profit increases. In real-world scenarios, although p of x tends towards infinity, this represents diminishing returns as the rate of increase in profit becomes very small as x grows larger. Hence, the maximum realistic profit is limited by factors such as operational costs, market saturation, and other constraints, despite the mathematical function growing without bounds. Let's dive into how limits of trigonometric functions can help us predict natural phenomena, specifically tidal heights. Tides are primarily influenced by the gravitational pull of the moon, and their rise and fall can be modeled using trigonometric functions. For instance, the height of the tide at a coastal town in meters above sea level at a time t hours after midnight can be modeled by the function h of t equals 3 plus 2 times sine of pi t over 6. In this function, h of t represents the height of the tide and t is the number of hours since midnight. Now let's answer some questions. First, determine the height of the tide about 6 hours after midnight. 2. As time goes on, what happens to the tide over a long period? Find the limit of h of t as t approaches positive infinity and explain what it represents in this context. To find the maximum height, we use the limit of h of t as x approaches 6. That is, the limit of 3 plus 2 times sine of pi t over 6 as t approaches 6. Substituting t equals 6 into the function, we will have 3 plus 2 times sine pi times 6 over 6. Canceling the common factor 6, it will result to 3 plus 2 times sine pi. Remember that sine pi is equal to 0. So we will have 3 plus 2 times 0. Simplifying, we will have 3. So the tide is 3 meters above sea level 6 hours after midnight. You can also visualize this by plotting the graph of h of t, where you'll see that at t approaches 6, the tide is indeed 3 meters high. To answer the second question, we'll look at the behavior of the sine function in the equation. The sine term, sine pi t over 6, oscillates between -1 and +1. Integrating this with the function h of t, we can compute for the minimum and the maximum height of the tide at t equals -1 and t equals 1, respectively. Substituting -1, we will have 3 plus 2 times -1. Simplifying that, we will get 1 meter. To get the maximum height, we substitute +1 into the function. We will have 3 plus 2 times 1. Simplifying further, we will have 5 meters. We can also answer the question by analyzing the graph of the limit of h of t as t approaches positive infinity. In the graph, as t approaches positive infinity, the curve oscillates between 1 and 5. This means that the tide continues to rise and fall, oscillating between 1 meter and 5 meters, but it never settles at a single value. Mathematically, we say that the limit does not exist because there is no fixed height that the tide approaches as time goes on. However, This oscillation represents the ongoing natural tidal cycle, showing how the tide constantly moves between these two heights over time. In summary, this is a great example of how trigonometric functions model real world periodic behavior and how limits help us understand their long term patterns. Stay tuned for more lessons on applying math in the real world.